So thank you very much. Let me just check if the slides are working. Okay, good. So thank you very much for giving me this opportunity. And also thanks to the audience for joining this session. So the theme of what I'd like to talk about today is to study algebraic geometry through via spectral invariants, and also study and the other way around, to study spectral invariants via algebraic geometry. And spectral invariants are some invariants coming from Flair theory, which I'm gonna recall shortly. Okay, so there are three notions that's been studied both in symplectic and algebraic geometry, which are singularities and degeneration and quantum cohomology. And the main tool, as I said, is the spectral invariants. Okay, so these four are going to be the key characters. So singularities, in algebraic geometry, I forgot to keep the time, sorry. So in algebraic geometry, people study algebraic varieties, and these things can be non-smooth. Like these things can have singularities. And there are many different types of singularities, but the most fundamental ones are called the isolated hypersurface singularities. This is an important class of singularities. And Arnold classified these isolated hypersurface singularities up to modality 2. So to an isolated hypersurface singularity, you can assign a positive integer called a non-negative integer called the modality, which roughly speaking kind of explains the complexity of the singularity. Okay, so all the isolated hypersurface singularities have like a non-positive, non-negative modality. So the modality 0 ones, the simplest ones, are called the simple singularities. It has, ADE type, 3 different types. And the next complex one, there are 3 types. So the first one is called the parabolic ones. Sometimes it's written with E6 tilde, E7 tilde, E8 tilde. Sometimes it's also called simple elliptic singularities. And the second type in the modality 1 ones are called hyperbolic. People often write it TPQR. And there's also this famous 14 exceptional singularities of Arnold. Okay, and beyond that, there's many, many, many higher modality singularities. And in this talk, when I say singular varieties, it's assumed to have at most isolated hypersurface singularities. There could be nastier singularities, but in this talk, we're only going to talk about isolated hypersurface singularities. Okay, so the second topic is degeneration. Okay, so in algebraic geometry, an extremely important question is to understand. So if you're given a smooth Fano variety, and you want to understand what kind of singular variety it can degenerate to, and this degenerate, when you say that a variety degenerates to a singular variety, it means that you have a family of varieties on, say, a complex plane, where the singular fiber is the central fiber is the singular fiber. And you see all the other fibers are regular, and you see somewhere the smooth final variety that you want to study. And if you have such a family, you say that X, this smooth variety X, degenerates to a singular variety X0. And understanding the type of singularities that can occur on a smooth variety is extremely important in algebraic geometry. In a minimal model program, they care about this a lot. And in the study of moduli spatial and enumerative geometry, this is also a very important thing. Okay. Oops. So up to now, we haven't discussed symplectic geometry. This is just algebraic geometry. So how do you get anything symplectic from this? So you need to be in a favorable situation. For example, I'm not gonna talk a lot about this, but for example, you have to have some nice ample line bundle on the total space or something. But if you're in such a favorable situation, then you can construct a projective embedding of all the fibers. And then by pulling back the Fubini-Studi form, you can start seeing the fibers as symplectic manifolds. And also, this allows you to define symplectic parallel transport on the total space, which allows you to, define vanishing cycles, for example. And it was Arnold and Donaldson who kind of noticed first that vanishing cycles of the singularities give Lagrangian objects in the regular fiber, provided that we're in this nice situation. Okay, so that's the connection between symplectic geometry and degeneration, which originally is a notion in algebraic geometry. Okay, and so for example, I said the simplest example of isolated hypersurface singularities is this ADE singularities, the simple singularities. And if you look at the vanishing cycles of these guys, what you get is a collection of Lagrangian spheres that have the intersection pattern as the Dinking diagram, ADE Dinking diagram. So for example, if you have an A singularity, AN singularity, and you look at the vanishing cycle of it from the procedure that I explained earlier, you'll have N Lagrangian spheres sitting next to each other. And each one of them intersect with the next one with 1 point. And for the DN singularity, once again, you get a collection of Lagrangian singularities, Lagrangian spheres intersecting just like you see in the Dinking diagram, and same for the E-type. And we're going to call these configuration, a collection of Lagrangian spheres, an ADE configuration. Okay. And so the two-dimensional case, so complex two-dimensional case, algebraic surfaces, has been studied a lot in algebraic geometry, but Arnold actually emphasized the importance and the interest of studying high-dimensional cases. Okay. But this, so high-dimensional cases are difficult to study in algebraic geometry because for the lack of methods, they kind of they study a lot the 2 and 3 folds, but it's difficult to say something about like high dimensional algebraic varieties. Okay, so now let me remind you what quantum cohomology rings are. So this is another topic that's studied both in AG and SG. So basically it's an idea coming from physics, and AG community and the SG community found their own kind of formulation, which is basically the same thing. But it's studied in both communities. And we would, today we're gonna define it as the, cohomology with this special coefficient ring field called the Universal-Novkov field, which we see often in Flair theory. Oops. And an interesting case is when this quantum cohomology ring is semi-simple. So the definition of semi-simplicity, we call that the quantum cohomology ring is semi-simple when it splits into a direct sum of fields. So now you have finitely many fields, Qj, which builds the quantum cohomology ring. And this specific algebraic structure of the quantum cohomology ring has been of interest, once again, in both communities, AG and SG. So for the AG side, there's a famous conjecture called the de Brovin conjecture, which is about giving conditions to when you have a semi-simple quantum cohomology. And Manin also studied this intensively, and Bayer as well. And in the symplectic community, Entov Polterovich found significant consequences to many different things. And I would like to just say that this semi-simplicity in AG and SG means something slightly different, but it's not like so different. I'm not going to detail that, but anyway, it's a structure that's been of interest in both communities. I'll give you some examples where you have this nice structure. So if you're interested in monotone symplectic manifolds, then the examples include the complex projective space, CPN, and the quadric hypersurface, Del-Pezzo surfaces, which I'm going to denote by dk, and k is the number of the points being blown up. Okay, and if the number of blowups is less than 5, then you get a semi-simple quantum cohomology. But if as soon as you blow up points at more than 5 points, then it's not going to be semi-simple anymore. Okay. And complex Grassmannians also have semi-simple quantum cohomology. And you can take products of the things I mentioned, and that would also give you examples. And if you don't confine yourself to monotone symplectic structures, then the toric Fano varieties, or many of the Fano threefolds, or you take a blow up of those manifolds, and you for a generic choice of symplectic structure, you get a semi-simple quantum cohomology. So you have nice examples like this. Okay, so now I'd like to state my first main result. So even though isolated hypersurface singularities and quantum cohomology are notions that's been studied both in AG and SG. It seems like there's no relation between them that's been known. And the first result says the following thing. So suppose you have a complex n-dimensional smooth Fano variety X, where n is even. And we assume either one of the two semi-simplicity condition. So either you have this monotone semi-simplicity, or you have this generic semi-simplicity. But if you assume the generic semi-simplicity, then you want the dimension to be higher than 2. Okay. So basically, the assumption is that you have semi-simplicity of the quantum cohomology. Now, suppose your variety X degenerates to a singular Fano variety with isolated hypersurface singularities. And then the outcome is that the singularity has to be of type A. So if your Fano variety has semi-simple quantum cohomology, then it cannot degenerate to D singularity or E singularity or the 14 exceptional singularity. All those are impossible to happen. You can only have type A. Okay. So in fact, so this is a completely algebraic geometry statement, but to prove this, you reduce it to the symplectic counterpart, which is the following theorem. But I'd like to just mention that this translation of SG to AG is not like immediate. You have to do some argument, but basically it's translation. So the counterpart is as follows. Suppose you have a real 2n-dimensional closed symplectic manifold, X omega. And once again, we assume that the quantum cohomology is semi-simple. And then you cannot have configurations of Lagrangian spheres coming from isolated hypersurface singularity that's not of type A. So you're not going to have, so once again, I put the dinking diagrams of ADE types. So theorem A prime is saying that you're not, like as long as your quantum cohomology is semi-simple, then you're not allowed to have Lagrangian spheres intersecting like the D type diagram or the E type diagram, that you can only have honest chains. Okay. So I'll try to explain some related works to this result. So first of all, I'm going to collect some algebraic geometry results that's related to this. So as I said earlier, kind of the surface, like two-dimensional case is fairly well studied and understood in algebraic geometry. So for example, the Fano case, so Fano surfaces are Del Pezzos. So the simple singularities that can occur on singular Del Pezzos were completely classified by Duval. This is a very classical work dating back to the 30s. And according to the classification of Duval, DE type singularities can occur for Del Pezzos with blowups more than 5 points. Okay. And let me remind you that in this situation, your quantum cohomology is not going to be semi-simple. However, if the blowup, the number of the points being blow up is less than 5, then the quantum cohomology is semi-simple, and Duval tells you that you can only have A-type singularities. Okay. So my result was for Fano varieties, but if you go to the Calabi-Yau case, then it's well known that, you know, D-type singularities, E-type singularities, the 14 exceptional singularities, all those things can appear in the degeneration of the K3 surface. And the K3 surface does not have semi-simple quantum cohomology. So all these things are compatible with my statement. And I'd like to emphasize that all these algebraic results in algebraic geometry, there's they're for surfaces. And because my method actually is based on symplectic topology, I don't have the dimensional constraints like in algebraic geometry. And this matches the perspective of Arnold. I told you that he wanted like high dimensional results. Okay, so that was some related work to algebraic geometry, but let me give you some related work to symplectic geometry. Yeah, wait.
So sure, are you using some kind of adjacency statement to get the result for general isolated hypersurface singularities?
Yeah, exactly. Yes, I will talk about that. Yeah. The answer is yes. Thank you for pointing out. Okay, so yeah, sorry. Compactive related works in the symplectic category. So here's an immediate consequence of the symplectic statement. So you cannot compactify a Milnor fiber of an isolated hypersurface singularity that's not of type A to a symplectic manifold with semi-simple quantum cohomology ring. And so, for example, Elsa Keating has a paper where she compactifies Milnor fibers of the parabolic singularities to D6, to del Petzls D6, D7, D8. And all these del Petzls don't have semi-simple quantum cohomology. So, you know, you can have these non-A-type configurations inside them. And also classical work of Dolgachev and Nikulin Pinkham, independently, they have papers where they compactify Milnor fibers of the exceptional singularities to K3 surface. And once again, K3 surface does not have semi-simple quantum cohomology. So these are once again compatible with my result. Okay, so when you have a semi-simple quantum cohomology, you cannot have D-E type singularity. You cannot have most of the singularities, but you can still have A-type singularities or like A-type configurations. This is still allowed, and this actually happens. You can find them, for example, in del Petzl surfaces. And if that happens, you have the following implication for the Hofer geometry, actually. And I'm sorry, but I'm not going to review Hofer geometry. So this next two slides are going to be kind of only for the experts, but I'm going to be out of this topic shortly. So please bear with it. So suppose once again, you have real 2n-dimensional closed symplectic manifold with even n. And your quantum cohomology is semi-simple. Let's assume that. Then if the symplectic manifold contains an AM configuration of Lagrangian spheres, then you can find m-1 linearly independent Entov-Polterovich quasimorphisms on the universal cover of the group HAM. Okay. And this answers some questions in Hofer geometry. So there's this famous question called the Kapovich-Polterovich question that's been circulating for like 20 years by now. And it asks whether if the group Ham is quasi-isometric to the real line R with respect to the Hofer metric. And this, even though it's been around for many, many years, extremely little is known about this question. And the expected answer is no. We want this group Ham to be big, but we only know the answer for S2 times S2, which was done by F.O. Cube and Eliasberg-Polterovich around 10 years ago. And then there was a long break in this on this problem, and it was the case of S2 was only confirmed 2 years ago by Cristoforo Gartner, Umidiel, Seyfedini, and Polterovich, Shalukin, independently and simultaneously. And a corollary of, so it's not an immediate corollary once again, but by using some other techniques and combining with the theorem B that I just mentioned, you can find 4 linearly independent Antonovics quasimorphisms on Ham of D4. And thus you can find a quasi-isometric embedding of R4 to Ham of D4, which answers the Polterovich-Kapovich question in the negative. Okay. All right, so we're out of Hofer geometry.
Yeah, but can you explain a little bit the new input? What is the, how did your theorem help with these?
Oh, so basically, this Polterovich quasimorphisms gives you, if you have one Polterovich quasimorphism, then you can basically say that there's a line going through Ham. Okay, it's an
yes,
this map is
your theorem is about proving that these are linearly independent. Am I
right? Yes. Yeah.
How does that work?
Let me answer that question after I prove theorem A, because that would be related. Okay,
maybe you could make a comment as to why, because your theorem said something about Ham tilde, while you have something on Ham. So is it possible to make a quick comment on how you go from Ham tilde to Ham?
Yeah, it's I basically
once you go from Ham tilde to Ham, it's done, I guess.
Yeah. Okay, so that's I use a result of Johnny Evans on the structure of Ham tilde, no, pi 1 of Ham. So it's it allows you to it descends automatically, basically, for this case.
Okay.
I'm sorry about not being super clear about the Hofer geometry part, because I didn't intend to spend a lot of time on it. But so once again, I'll go back to Umut's question after I at an appropriate point. All right. So okay, so the key ingredients of the proof of theorem, all the theorems that I mentioned, there are 2 things. So the first one is the theory of asymptotic spectral invariants due to Polterovich. So, you know, they have this nice theory of quasimorphisms and super heaviness and all that. And the second input is Biran-Members' Lagrangian cubic equation. Okay. And so once again, I'm not gonna prove theorem A. I'm just gonna mention that it follows from theorem A prime, which is its symplectic brother, after some AG argument. Okay, so I'm gonna briefly summarize this theory of Polterovich and Biran members. Okay, so Anton Poltrovich built their theory. It's based on Viterbo's spectral invariant theory. And these things are actually, they're powerful tools to study the Hofer geometry and Hamiltonian dynamics. It's been developed by many people. And the construction goes as follows. So you start from a Hamiltonian H on your symplectic manifold, and you build a filtered Flair chain complex. Okay, so it's filtered with respect to a real number tau, and you only pick up the generators that have action less than tau. Okay, and then this gives you a filtered Flair homology group. And there's also a map, natural map coming from the inclusion on the level of the chain complex. And we also have this nice PSS map that relates the quantum cohomology to the Flair homology of H. And now spectral invariants, so they're numbers, they're real numbers assigned to a pair of Hamiltonian and class in quantum cohomology class. So the spectral invariant of H and A is defined as follows. So it is the real number where you start seeing, it's the action level, sorry, where you start seeing the class of A corresponding to the Flair group via the PSS map. Okay, it's a certain real number. And you can do the same thing for Lagrangian Flair theory. And I'm going to denote it by like curly L. And this, I'm not going to precise the class of quantum cohomology that we're taking, but it's if I write such a thing, it's only for the fundamental class. Okay, so Anton Poltrovich introduced a notion of symplectic rigidity called the superheaviness. So by using the spectral invariants. So Anton Poltrovich actually introduced heaviness and superheaviness, but in this talk, I'm only going to talk about superheaviness. Now, what is superheaviness? So suppose your quantum cohomology has a field summoned. It splits as sum of Q and A. And you decompose the unit with respect to the split. And so now you have 1 equals E plus E prime. And then you define the asymptotic spectral invariant of this idempotent E in the following way. So you look at the spectral invariant of K times H with respect to the unit of the field summon E, and you look at the growth. So you divide it by K and take the limit. And this is well defined. It will give you a real number. And I'm going to call this function zeta E. Okay. And now, given a subset S inside X, we're going to call it super heavy with respect to the idempotent E if the following property is satisfied. So you look at the value of the asymptotic spectral invariant of E with respect to the function H, the Hamiltonian H. And then super heaviness allows you to actually control the value of this zeta asymptotic spectrum invariant just by the value it takes on the set S. So if you can bound, if you can say that your asymptotic spectrum invariant it's somewhere between the smallest amount H can take on S and the biggest amount it can take on S, then you can say that this set is super heavy, okay? And a side remark, you can define the asymptotic spectral invariant of Lagrangian Floer homology in the following, in a similar way. And the following is going to be a super useful property when you deal with these super heavy subsets. So the lemma says that there's no disjoint sets that are both super heavy with respect to the same idempotent E, okay? So, so this is actually a very easy statement. So suppose, so argue by contradiction, suppose you have two disjoint subsets that are both super heavy with respect to the same idempotent E. Now, you can take a Hamiltonian that vanishes on the set A, and that's constantly equal to 1 on B. Then, as I said, by definition, you can control the value of the asymptotic spectral invariant for H by looking at what value it takes on the sets A and B because of superheaviness. And then you can bound it from below by 1 because it's constantly 1 on your set B. And also you can bound it from the above by 0 because H is constantly 0 on A. So now you got a contradiction. So therefore, we prove the lemma. So there's no disjoint super heavy subsets, okay? All right, so this is a very easy but useful property of super heaviness. So now the second key ingredient of the proof is the cubic equation due to Biran and Membres. So the statement is as follows. So once again, you work in a real 2n dimensional closed symplectic manifold. And here I don't assume semisimplicity. They don't assume semisimplicity. And suppose you have a Lagrangian sphere inside there. And this will define a homology class. And you see this homology class or a cohomology class by taking the Poincare dual is a class of the quantum cohomology ring. And what they proved is that you take the power of 3, and then it comes back to itself with some coefficient, some multiple, okay? And so obviously if this coefficient is 0, then it means that the class L is a nilpotent. But if it's not 0, then this cubic equation implies that you get the following two idempotents. So I wrote down the precise description of EL plus and minus, the two idempotents that are produced by a Lagrangian sphere. So it means that if you take the power of 2, it goes back to itself. It's an idempotent. But actually, you can say a bit more about this. It's not just they're not just idempotents, but they're actually units of field factors. So that means that you multiply it to the whole quantum cohomology ring, and then you get the universal Novikov field. So it gives you a field summoned. Okay. So to summarize the previous slide, if this coefficient is non-zero, so if the class L is not a nilpotent, then you get two unit of field factors, which gives you two Entov-Poltrovich asymptotic spectral invariants, zeta of E ln plus minus. And we assume that if we assume that the quantum cohomology is semi-simple, then it means that there's no nilpotence. So this would automatically imply that this coefficient that we have is non-zero. Okay. So as a result, if we are in a symplectic manifold that has a semi-simple quantum cohomology, then for any Lagrangian L, we always have this two Antonovics asymptotic spectral invariants, E, L, and plus minus, zeta of E and L plus minus. So I just drew a figure that tells you that, in this setting, given any Lagrangian sphere, you get two units of field factors, EL minus and EL plus. Okay. Okay, so now I'll tell you two lemmas that's going to be that's going to allow us to prove the theorem. So the first one is called the idempotent sharing property. So suppose you have two Lagrangian spheres that are intersecting, so homologically, or it shares a point or whatever. Let's say homologically. Then, as I said, each of the Lagrangian spheres gives you two idempotents, right? And the claim is that if the Lagrangians are intersecting, then one of the two idempotents has to be shared. Okay. So I drew a figure that basically explains the situation. You get two from each one of them, but if you have connection between the Lagrangians, then one of the two has to be shared. The yellow ones in the figure. Okay. This lemma I'm going to call the idempotent sharing property. Okay. And the second lemma is that the Lagrangian L, so if you have a Lagrangian L, you get two idempotents. And the Lagrangian sphere is super heavy with respect to both of the idempotents that you get. So that's the second lemma. So once again, L, like as soon as you have a Lagrangian sphere, it's super heavy with respect to two of the idempotents that it produces. Okay. So now let me prove theorem A. So we start with the simple singularity case. So we have ADE singularities. And let me remind you that the claim was that I don't want any DE configurations inside the symplectic manifold. Okay. And the DE configurations, once again, it looks like this thinking diagrams. And okay, so what's the difference between A diagram and DE diagram? So what is the difference? So the difference is that you can find a Lagrangian sphere that intersects three other Lagrangian spheres. So I drew a figure on the right-hand side. So you have the central Lagrangian S that's intersecting S1, S2, and S3. And you cannot find such a configuration in the A-type diagram. Okay. So now the proof basically uses the fact that 2 is not equal to 3. So by the idempotent sharing lemma, S, the central sphere, shares an idempotent with each one of the surrounding ones. But let me remind you that each of the spheres only produce two idempotents. Okay. So you have something like ES minus equals ES1 plus, and ES plus equals blah blah blah. You have this kind of idempotent sharing properties. But the thing is that 2, which is the number of idempotents that's produced by S, is not equal to 3, which is the number of spheres intersecting S. So this tells you that, either one of the S minus or plus has to be shared by two of the spheres, S1, S2, S3. But then all the spheres, S1, S2, S3, they're all disjoint. And how can they share an idempotent if they're all, so for which they're super heavy and they're disjoint? So this is a contradiction. Okay. So this, so thanks to 2 not equal to 3 property, you don't have any DE type singular configurations. And so the higher modality case, going back to the first question of Umut, once again, we want to kind of know the Dane diagrams for these singularities, but thankfully these things are known thanks to works of Gabrielov and Elsa Keating, but we don't know the full thing. Like Keating studied she really studied she understood the Dane diagram completely for some modality 1 singularities, but for the higher modality things, you don't really know exactly what you have. But as Umut pointed out, you have this I can't say this, adjacency property that tells you that you can see part of the modality 1 Dane diagram is embedded to the higher dimensional, higher modality Dane diagram. So actually you can find similar nasty configuration that you want to rule out. And you can complete the proof in this way, okay? So that's the proof. And I think I want to go back to the second question of Umut. So in the statement where I spoke about Hoffe geometry, so and distinguishing Entop-Poltrovich quasimorphisms. So first, one thing is that if you can find linearly linearly independent Entop-Poltrovich quasimorphisms, then because each one of them are Hofer-Lipschitz continuous, you can say that you have linearly independent lines, like roughly speaking lines, in the group Ham. But then how do you argue that those quasimorphisms are linearly independent? So in order to do that, once again, I want to use the no disjoint super heavy sets property. So then if you have an AM singular configuration, so you have M spheres sitting next to each other, you can say that M-1 of those idempotents give rise to different Entop-Poltrovich quasimorphisms, because you can find basically 2 spheres that's disjoint. So not managing to explain this clearly. Basically, because of the sharing property, idempotent sharing property, even if I actually deleted the slide where I explained that. So yeah, roughly speaking, by combining the idempotent sharing lemma and the disjoint, non-disjoint superheaviness lemma, you can find disjoint spheres according to the idempotents that you want to talk about.
So I think I get the idea.
Okay, good. Yeah, well, thank you. I'm sorry.
No, it's good.
All right. So I want to, so the last thing, I want to finish my talk by telling you the last statement, which is about the relationship between the Dane twist and spectral invariance. Okay. So, recall that, finding AM configurations, it was the starting point of the study of Seidel to, derive many, many interesting things about the Dane twist. So he always started from finding a AM configuration. So then, we've been talking about spectral invariants and Lagrangian spheres, and Seidel talks about Dane twist. So a natural question is, what effect does the Dane twist have on spectral invariants? Okay. And the statement is that basically it reduces the spectral invariant. So the precise statement is that, once again, same setting, you have a closed symplectic manifold, and this quantum cohomology is semi-simple. And now suppose you have two Lagrangian spheres forming an A2 configuration. And then you look at there's a Dane twist coming from the Lagrangian L, and you can twist the second Lagrangian with respect to with the Dane twist, and you get a new Lagrangian sphere. And now I want to compute the asymptotic spectral invariant of this Dane twisted Lagrangian sphere. And the claim is that it's not going to be more than the maximum of the asymptotic spectral invariance of the Lagrangian spheres that's involved in the procedure. So L and L prime. Okay. So I'm not going to prove this entirely, but I'm going to just pick up some key points. So first of all, I'll remember that each Lagrangian sphere gives you these two units of field factors, EL and plus minus. Okay. And so by using the Picard-Lefschetz formula, you can express what the corresponding idempotent for the Dane twisted sphere would be. Okay. And what you actually learn from it is that the Dane twist switches, it swaps the idempotents. Okay. So I drew a small figure over there so first you have two Lagrangian spheres L and L prime forming an A2 configuration. So you have two idempotents from each one of them. And then by the idempotent sharing property, one of them has to be shared, right? And now what the Dane twist does is that, so first you look at the two idempotents produced by L prime. You have two things, and one is shared with L. But the Dane twist coming from the sphere L swaps the thing that's been shared to the non-shared one. Okay, this is what the Dane twist does. And I said earlier that you can express the asymptotic Lagrangian spectral invariance in terms of the asymptotic Hamiltonian spectral invariance. So by using all these three things, you can complete the proof. So I'm gonna just summarize the talk. So the first thing, you can prove algebraic geometry results by using spectral invariants. That was theorem A. And sometimes algebraic geometry can tell you something about Hopf geometry. So that was theorem B. And the third thing is the Dane twist reduces spectral invariance. Okay. So Basically, I spoke about those 3 points, and that was all I prepared. Thank you very much for your attention.
Thank you, Yusuke. So are there any questions?
Maybe I have a couple of questions. So my first question is the following. So can you say something about degeneration of things which are not semi-simple but have certain constraints on the number of field factors?
Oh yeah, I don't know at this point, but that's definitely the next step. That's definitely the next step. I don't know.
Because my impression is that this Delpezza surface is kind of even higher, so field factor they have.
Yeah.
But maybe you can say that it should not be more than this amount of field factors if you want to give this type of singularity in the degeneration.
True. Yeah. True. That's true. That's one future direction that I had in mind, in fact, and at this point I don't have any interesting observation, but yeah, I will tell you if I come up with anything interesting, definitely.
Interesting, thank you.
Could you explain again this cubic equation that you used?
Yeah.
So is it applying to any Lagrangian sphere in any? I mean, I kind of missed.
You just have to be careful about the dimension a little bit because, so yeah, you only have to be careful that you're in a 2n real dimensional symplectic manifold with even n, because when n is odd, sometimes you don't get non-trivial, cohomology class. The sphere sometimes defines it. It's null homologous sometimes.
Okay.
But yeah, but
so,
otherwise,
so it's pretty general result. So
yeah, this is general.
Yeah. Okay, I didn't
so
know.
Here, there's no semi-simplicity or anything.
But maybe you need some monotonicity or something. No.
So Biran and Members actually proved it under monotonicity, but it was generalized by Sanda afterwards.
Ah.
Yeah. So yeah, I should have pointed that out. Thank you very much for. Yeah, it's Biran Members' original statement was under monotonicity.
And for this estimate you had for the Dane twist,
yeah,
I might have forgotten the conclusion. The conclusion was that the spectral invariant for the Dane twist is can you prove it is equal to the maximum or it's less or equal to the maximum?
So I don't know the answer. But
because you have a triangle.
Yeah.
And to me, it would feel like maybe it is a maximum. But
maybe,
okay.
Yeah. So actually, I know when I did this, I obviously thought about your work, and that's done in the open setting, for open symplectic manifolds. Exact. So it's not exactly my situation.
No, it's not. No, it's different. Yeah, it's different.
But I wanted to first of all see if you get the same relationship in your setting by using your filtered Dane twist triangle. That's one thing I will do, but I just didn't,
No, but I'm just curious. Maybe maybe it's easy actually the maximum and not only smaller radic. I don't know. I don't know, but I was just curious. Maybe
Yeah, I don't know the answer, but you're right. There's fair reasons to expect that the equality should hold. Yeah.
Because I mean, if you have strict inequality, you can start iterating in different orders.
So that's what I was saying,
Yes, and it would be kind of indeed spectacular. So you have some quantity which decreases along the action of mapping class group, kind of.
Yeah. think, yeah, double check.
Yeah, but I mean, maybe there is something kind of really
Yeah.
unexpected here. Yeah, so, okay.
And I have another question. So I know you didn't want to speak much about your Hofer geometry result, but
yeah.
But somehow,
yeah, I just thought, yeah, so I just thought I would run out of time, but I had time. So yeah, now it's okay.
So how does the D4 enters appears here? Because I mean,
I didn't understand your question.
I mean, so you have a result on D4, but
oh,
then
yeah,
you're
D4.
using, but then you're using Lagrangian spheres, so I'm a bit confused how. There's a step I'm missing, I think.
Oh, this is the corollary that you were talking about.
Yes.
Yeah. So in D4, you basically you're asking how I get this corollary from the theorem B.
Yeah. Yes. Maybe that's.
Yes. Yeah. So yeah. Okay. So it's not an immediate consequence of theorem B, because theorem B says if you have an AM singularity, then you have M-1. So in D4, you can find an A4 configuration. That's true. But then that would only give you 3, right?
Really? Wait.
Yeah, in D4, you have A4.
Sorry, what is D4?
It's a 4-point blow up of CP2. So it's the Petzl surface.
Okay. I misunderstood. For me, D4 was like the ball or something.
No, sorry. I know that people don't like this notation.
It's okay.
Yeah. Sorry. So this is a De Petzl surface blown up by 4 points. Blown up at 4 points. And so just to say a few words. So like D4 does admit A4 configuration, but the theorem of B would give only 3. But how do I get 4? So it actually start from another toric degeneration that gives you a torus, a Lagrangian torus, and an A2 singularity and an A1 singularity. Okay. So then what you can do is that so in this situation you have a quasimorphism coming from this torus, and you have 2 other spheres. But then you can find, so there's a nice work of Li and Wu that allows you to construct Lagrangian spheres with some minimal intersection property. This is a 2-dimensional technique. So you actually can complete the A2 singular configuration and the A1 configuration into an A4 configuration. So you find the missing Lagrangian by this 2-dimensional technique by Li and Wu, and then you can apply my thing, and you see 3 there. So it's 1 from the torus, 1 plus 3 from the completed A4 configuration.
Okay, thank you.
Yeah.
Is there any other question?
Yeah, I'm sorry because I missed. Hi, Yusuke.
Yeah, hi.
I'm sorry I missed the beginning of your talk, so maybe my question will be answered. Was answered at the beginning of the talk, but what I understand is that your theorems are about configurations of Lagrangian spheres and have nothing to do with singularities in a way. I mean, you apply them to singularities, but what you say is that if QH star has a certain algebraic structure, then a certain configuration of Lagrangian spheres cannot happen in your symplectic manifold. So if you take other examples of other graphs, I mean, not just the one that appears with a point and 3 connected edges, you have other graphs for which you can say, well, if QH star has a certain algebraic structure, then this configuration of sphere cannot happen. Maybe that was in the beginning of your talk, I don't know. But...
so first of all, you said like a priori spheres and the singularities have nothing to do with each other. But
no, of course, in one direction, of course, it's obvious.
Yeah.
What I mean is that there's no reason to restrict to the AD diagrams. You could think of other diagrams, I guess, represented by Lagrangian spheres.
Sure. But I cover all the isolated hypersurface singularities.
No, I understand. No, I'm not criticizing.
I know. But I don't know the other.
Can you relax the semi-simplicity to something else so that you are able to get a weaker result? Is that the question?
No, that's not my question would be more about banning other graphs than just the one that appear as Dean diagrams.
We just start with plumbing of many spheres according to some pattern.
Yes.
And then ask how you can compactify this. So so what Claude said, that Yusuke's theorem yields some abstractions on quantum cohomology of this compactification. Right.
Yeah, right.
Yes, yes, exactly. That's what I.
Yes, but isn't such every graph which is not a tree, doesn't it contain the configuration that Yusuke eliminates? Isn't there always, or maybe there's just cycles, sorry.
No, you could have can you have a triangle, for example?
Like a cycle, yes, okay. So
yes,
you
or
can have,
cycle.
Yeah, so I think
there's not much else.
Yeah, right. So actually triangles, it can, the pattern of the Dinking diagram, it depends on the way you sort of construct the vanishing cycles. Because, remember that for a given singularity, what you do is that you morsify it, and then you pick like a regular fiber, and then you choose a path between them. And, so there's a certain, you can get different intersecting patterns depending on.
I'm probably missing out something. It's of course an interesting case to look about singularities, but why do you only want to look at Lagrangian configurations that come from singularities?
Because
things that do not come from singularities, I guess, no?
True. That question makes sense and it's interesting. But my original motivation was to get some results about algebraic geometry. So
it's probably the most interesting case. I mean, that's not the issue. I just wonder if you can say something about cases which do not come from singularities.
I
don't necessarily come from singularities. I have the impression you have a rather general tool that sort of says something about configuration and the fact that this one E plus is the other guy's E minus and this kind of thing seems to be powerful. Maybe can give.
So there is a part in what you said, Yusuke, which is independent of where the configuration comes from.
Yes.
So if you look at the Lefschetz vibration and you put your, vanishing cycles and how's this called, connecting spheres, or in the positions that are similar to diagrams that you can easily describe, but more general than the ones coming from singularities, we immediately get consequences for the ways you could compactify this space to a symplectic manifold. And so you would deduce that certain things don't admit compactification. So I mean, there are many things more that for sure that you could say, there's no doubt.
Right, yeah. I need to think about that more. Yeah, you're right.
Because on the symplectic side, this construction of Lefschetz vibration is very flexible. You can really do any configuration basically you want. You can have one vertex and many spheres at a Batzer, and then you can apply again your argument and so on.
Mm-hmm.
Right, but I think his argument really relies on spheres intersecting once.
Yes, spheres that intersect in one point. But what I'm saying is that you can have.
You have anything that's that different? I mean, if you require the spheres to intersect at most once. If the valency of every vertex is less than 3, then it just has to be a cycle.
But you could have a cycle, and you also
that's okay. That seems interesting. Yes.
You could have cycles, and you could go valency higher than 3.
But
for which his argument would still apply for valency
Yes,
bigger than
if you-
3,
Yeah,
because it's the
yes,
same.
but it's already eliminated, right?
Yeah,
That's
it's already,
eliminated, yes.
I mean, it's not eliminated. It tells you that the compactification is not semi-simple. So if it exists or whatever.
Yes.
Maybe we could decide it's the end of the official discussion, and thank Yusuke, and we can continue again. So thank you very much, Yusuke.
Thank you very much. Thank you.
And I mean, we can continue the discussion now.
And I have an official question. So in this controversial D4, which is not a disk, but a Delpetto surface for blow-ups, can you somehow apply this method by FO3 with bulk deformation and get kind of more quasimorphisms? And so then instead of kind of embedding of R4 into Ham, you will get kind of, you will at least embedding of R infinity.
I don't really know. I don't know. I start to think about that, but I'm still slightly uncomfortable with the bulk deformation. So
because in principle, maybe even this Beran-Membres equation can be generalized into bulk setting.
yeah, you know, I did think about that because the notion of semi-simplicity in AG and SG is slightly different, as I said.
Yes.
And in AG, you know, in the sense of Manin and Dubrovin, they look at big quantum cohomologies. And so that's why I was thinking if the, you know, so in the big quantum cohomology setting, what can I say? So, but I still don't really know.
I see.
But I do, yeah, I do have in mind that case, definitely. Yeah.
But like about this relaxing the conditions thing, so can you, for example, not relax to the case where just you look at the even part of quantum cohomology and that's semi-simple and you don't have to require anything about the odd part, for example?
Well, there's actually, if your quantum cohomology is semi-simple, then there's no odd parts.
Yeah, I know. So let's, I'm saying let's relax that and just say, okay, the assumption part is
I see.
simple, but the odd part we say nothing.
I haven't thought about that.
It's not like I have many examples. I think that they exist. I think.
Sure, it should exist. Like the Pezzo probably in the high blowups, it is such an example.
Yeah. Oh.
So.
But you said that there are counterexamples in that.
Sure. Yeah. In that case, there's a DE configuration. So yeah, I don't have any result relating structure of the quantum cohomology beyond beyond semi-simplicity and the existence of configuration, but yeah, I don't know. Yeah, it's an interesting question. I want to study more about the relation between the structure of quantum cohomology and possible singularities or configuration types it can have, but at the moment I don't know so many things. Yeah.
Great. Thank you. It's a great result. I think I don't know. I hadn't heard anything like this before.
Thanks.
Bye-bye.
Thanks a lot.